Before we get into calculus and volumes of revolutions, let's just take a step back and think about some of the volumes that we know. And a formula that's really going to help us understand what's happening here is just thinking about a cylinder. So if you have a cylinder, okay, what's the volume of that cylinder? If this is my height, and that's my radius. My volume is, okay, pi r squared times h. Now, if we break down that formula, can you see that that formula is the area of a circle times by the height? And we know that volume is what fills in a shape. And so if you think about having one circle here on the bottom, and today I'm going to use lots of crayons. Because crayons are fun. So I have that one circle. If you think about cutting a piece of paper and putting it into that cylinder, it would not fill up the whole thing. But if you kept adding pieces of paper all the way up, I don't know if this is going to work. Whoa, that one went too far. That one went too far. All right. So if you kept adding these circles and stacking your paper all the way up, yeah, that's a pretty light stack. There would probably be a lot more pieces of paper there. But that all of those papers stacked on top of each other would eventually fill the whole cylinder. And so our volume is area of the base, which is a circle, times by the height, because sort of that's like how many stacks of paper you would need to get all the way to the top. So now we're going to get into volumes of shapes that we don't have formulas before. So this first one is going to be the easy one, then we'll get to more complicated stuff later on. But to start off with, if I had a curve, f of x, and maybe this curve almost looks like 1 over x. What I could do is I could take any point along here, and if I was rotating that point around the x-axis, can you see that that would make, oh, I got to take out a crayon. It just does not work as well without crayons. Can you see that that would make a circle? And depending on which point I use, like if I use this point right here, that would make a bigger circle. And so as I move along the curve, I have a bunch of different circles to do and a bunch of different circles to make. Now, if we added up all of those different circles of different radiuses, we would get the volume of that shape in total. And so we use what we know about integrals and combine it with this idea of rotating something 360 degrees around, because our integral finds what? Our area under a curve, right? And the integral finds that area under the curve by making rectangles smaller and smaller and smaller and smaller. And if you make a rectangle infinitesimally small, can you see that it just becomes a straight line like the radius? Then if you use that radius and do a pi r squared with that radius, you get the area of that circle. And if you add up all those areas of that circle, you can get a volume. And that is the idea behind a volume of revolution. What we're doing is we're taking an equation, so a solid of revolution is formed by revolving a plane region about a line. So if you take an equation like f of x, and you imagine finding the area under the curve of f of x, so that would be this area, and I take that area and wrap it around the x-axis, it would fill in a volume. And that is called a volume of revolution. Now, what we can also do is you could find, just like areas between curves, you could find one volume of revolution and then subtract a volume of revolution, and we can figure out something like you see here, which is, can you see that when that's put together, that volume of revolution kind of makes a bell? And now we can create a formula to find the area of a bell. If you can create an equation that models the outside of the bell and create an equation for the inside of the bell, then you can just take the volume of one minus the volume of the other, and you'll have a formula for the volume of that bell, which is really cool because the shapes are not pretty, but the shape in the end is something we've seen. You can see that, okay, if I was a, I don't know, are there bell makers? People that are specifically, there probably are specialized bell makers for churches in Europe. I don't know if they're in business very much anymore, because bells last a long time. Except for, isn't that the famous one in Philadelphia has a crack in it? Anyways. So let's look at what the formula is. It's just the integral, right? Can you see the pi r squared in the formula? The integral could go here, but because pi is a constant, you could pull it out in front. And the radius, we talked about the integral, finding that area under the curve. Well, your radius just becomes that point on our function. I think on your formula sheet, they might have y instead of f of x. All right, so what does this look like, and what can we find? Find the volume of solid generated when the region under y equals x cubed from 1 to 2 is rotated about the x-axis. Now, for me, the most fun in this unit is drawing it out. So what does our x cubed graph look like? Well, it's got 0, 0, 1, 1, negative 1, 1, 2, 8. Wow, is that flattened out enough? I said I like drawing it, and then I just go and butcher that. Okay, we're going to try that again. That's better. Oh, yeah, that's much better. And we're trying to find this volume from 1 to 2. So we've got the point 1, 1, we've got the point 2, 8. That would be the area under the curve. And now I got to imagine rotating that 360 degrees around the x-axis. So I'm going to go to 2, 1, 1 down here, 2, 8 right down there. And for drawing purposes, I'm going to try and draw little mini circles to show the revolution around. Now, for visualizing this even more, this is where I like to use the crayons. I like to color things in. So if you were looking at this, can you see that this purple circle here is like the circle that you could see from the side, and then you would just be able to see the orange part here is sort of the side of it. The purple part, if you wanted to put it down, could be the bottom, and the orange part could be the sides. So we've kind of got like a, I mean, it's a solid, but kind of like a big horn thing that could amplify your voice if you wanted to. So now what's the volume of that shape? Well, we can find our volume, right? Our volume says it's going to be pi times our function, which is x cubed squared dx. So all of our radiuses of those circles that we're going to get are from the equation x cubed, and your formula for a circle is pi r squared, and adding up all of those circles from 1 to 2 will get you the volume. So this is the definite integral from 1 to 2. It's going to be x to the 6th. That's a really easy integral to figure out. Add 1 to the exponent and divide. So notice I'm keeping my pi factored out. With your definite integral, you do 1 subtract the other, plug in 2. 2 to the 7 is 128. Plug in 1. And we get, or 127 pi over 7. Which just looks like a nice number. I don't know why. Maybe all the 7's in there. The fact that it has pi, the fact that we found that volume without a calculator, yeah, 2 to the 7 was pretty high, but it is quite amazing because the shape that we looked at didn't look like any kind of nice shape that we know. Was there units involved in this one? No. Up that far? Is that? The curve, the square root of x minus 1. So again, we can draw. That is just your square root graph shifted 1 to the right. So you'll have 0, 1, 2, 1, 5, 2. And we want to find the area. Oops, not 0, 1. Thank you for being so kind and not saying anything. 1, 0. So that square root graph has been shifted 1 to the right, and we want to find the area up to 5. So if we take that part and rotate it 360 degrees around the x-axis, we would have a point down here. The curve would be reflected over, and we would draw a circle. I'll do it. And again, to really see this volume, oh, I got to use the right colors here. We're going to go red for this part and a dark orange. Oh, and I call this the ham graph. Yes, doesn't it look like a big chunk of ham you could buy from Superstore? So now if you wanted to find the volume of ham that you just bought, and you happen to figure out that, hey, it's just a square root graph rotated 360 degrees about the x-axis. Well, we can set up our volume formula. Integral from 1 to 5 Square root of x minus 1, but that gets squared. This is going to work out so nice. What happens when you square a square root? Well, not nothing. It just goes away, but yeah. Oh, the squared would be gone. Beautiful. And again, it's a really easy integral to figure out because it's going to be add 1 to the exponent, divide, going from 1 to 5. We have 1 minus the other one. So plugging in 5 will give us 25 over 2 minus 5. Plugging in 1 will give us 1 over 2 minus 1. Mental math, what's the fastest way to do this in our head? Okay? You could change everything to decimals right now. I personally would do the 25 over 2 minus the 1 over 2 right away because you have a common denominator. What does that give me? 24 over 2, which is 12. And then it's going to be 12 minus 5 plus 1. One ham is equal to 8 pies. Is that true? If you go to a store, the cost of 1 pie compared to the cost of 1 ham, is a ham 8 times as expensive? It's probably due to this. I'm sure that's how they decide the prices. Not, you know, what they say in economics about supply and demand. No. It's all based on volumes of revolution instead. Oh, yeah, very cool. And again, the crayon. Crayon just puts it up that one level. Find the volume of the solid that's formed when the region between y equals sine x and y equals cos x from 0 to pi over 4 is rotated about the x-axis. Okay. I'm going to draw more of my sine graph than I need to, and then take some of it away. So a sine graph goes from 1 to minus 1. We just need to go to 0 to pi over 4, but you're probably really used to graphing all the way to 2 pi for sine, right? And so pi over 4 is right here. How does the sine graph go? There's our sine graph. Our cos graph, same thing. Graphed it from 0 to 2 pi because that helps us graph it. But we're really only looking for, okay, what we're looking for is this part between the blue and the black graph, the area between the curves, rotated 360 degrees around. So what we could do, okay, is imagine the volume under the blue curve. So if you took the blue and the blue curve go like that. Again, I'm going to color code this, okay? I'm going to take out my crayons. I think I might have to go to I'm going to color the circle in here with a black crayon. Okay? And then I'm going to fill in that line there, and I am going to color in with crayon. So that volume, which I'll write in blue, 0 to pi over 4, that's my cos graph squared dx. Now, if I only wanted the volume between the cos and the sine graph, can you see that I would need to erase or take out the area or the volume under sine? So again, I'm going to color over top here. I think I need to go to like a light gray. There we go. Can you see? No. Well, maybe. If I see, the beauty of crayon is the wax just goes over top of other wax eventually. So that gray part would have to get subtracted. So we would need to subtract. I'm having so much fun with colors today. No. Here we go. We need to go back to pen. Can you see if I write in gray? Oh yeah, that shows up. And we need to subtract the area from 0 to pi over 4 of sine x all squared with a pi in front dx. If I subtract the silver part, that silver volume, out of the blue volume, I will get the volume in the end. Now, to best see that volume in the end, I need to color over top more in blue, right? That's what it would look like. Can you imagine? It's like a dog dish turned on its side. If you want to design like high-end titanium dog dishes using sine and cos curves, this would be your formula. Okay? There is, unfortunately, right here, a minuscule hole right at the bottom. So if you were pouring water in, as long as that hole though would have a area smaller than anything, because it's just a pixel, not even. So water molecules would probably still be too big, they wouldn't fall through. So I think you're fine. So this is what we have. Now, when we look at this equation the way that it is right now, okay, you cannot do the integral of cos because it would be a chain rule with the squared, and there's no substitution that you can do. Same thing with sine squared. We can't integrate sine squared by itself because it's a chain rule, and we'd have to use integration by substitution, but the derivative is not present. So it appears at this point that things are not working well for us. However, if we use the properties of algebra, I could factor a pi out of the whole thing. Can you see that? There's a pi in common in both those terms. And then I would just get one integral minus another integral. And from calculus and the properties of integrals, we know that minusing one integral from another can be done, whoa, inside together. So I could put those two integrals together, which currently, the way that it's written, would still mean I can't do anything, because I would still have to integrate cos squared by itself, which I can't do, and sine squared by itself, which I can't do. So here's where I need you to get creative. Musa, what could we do? You look like you had an idea. Okay, you're looking at the identities up here, and you're looking at sine squared plus cos squared equals 1. But this is minus. Okay. Oh, Devin has an idea?
So you could move this sign to the other side and then substitute, like for the identity.
You could use a sign to the other side and substitute, true, and then I would get a 1 minus cos squared for the sine squared. If I distributed that, I would still end up with a cos squared in my equation, which doesn't allow me to do an integral because it's a chain rule. Unfortunately, with that negative sign in there, the sine squared plus cos squared equals 1 identity is not going to help us, because no matter how we try to rearrange it, we're still going to end up with just sine squared or just cos squared. But there is another identity up there. There is one that says cos squared alpha minus sine squared alpha is cos 2 alpha. And if we did that identity, this is an integral we can do. Integrating cos, will it be positive sine or negative sine? Positive sine. And since this would be a chain rule where you multiply by 2 when you did the derivative, when integrating, we need to divide by 2. Super cool. I'm going to find out how much titanium you need to purchase for this dog dish. Like for putting dog food in. It's a dish for dogs. How do you say it in French? Something de chien? Okay. And now we can plug this in. Oh, this is all unit circle. Beautiful. What happens when you plug in pi over 4? What is sine of pi over 2? 1. So this one will become 1 over 2. What is sine of 0? 0. And so we get 1/2 minus nothing times by pi. The volume is pi over 2. So cool. And there was no units here, but whatever units you chose, right? Right, when going to make your dog dish, you'd figure out, well, what kind of base, how big do I want to make this base? If I want to make this 10 centimeters, well, then we could figure out. Now you can see the dish? Oh, I thought my crayon drawing was pretty good.
I didn't know what a dog dish was.
Okay. There we go. Perfect. Beautiful.